In this video, we're trying to integrate the inverse cosine function, which some of you may know as the arccosine function. It's the same thing. And the trick to these is to undo the inverse trig function immediately with your first substitution. So here I go. If I let x be cosine theta, then I'll have inverse cosine of the cosine of theta, and those two will undo each other. And immediately my integral becomes something simpler. Remember, you will have to transform the differential of x as well, so I've got to do that. And I get negative sine theta d theta. And the last thing I want to prep for here is that at the end of the problem, I'm going to have to sub out and replace theta in terms of x. So I may as well prep for that right now. Theta is the inverse cosine of x. So I rewrite my integral, replacing x with cosine theta and dx with negative. I'm going to move that in front. The minus sign is in front. Sine theta d theta. And the inverse cosine of the cosine, well, those undo each other, and I just get theta there. So theta sine theta d theta. Now this is a classic integration by parts problem, so I'm going to have to make those substitutions next. I pick u so that it becomes simpler when I differentiate it. So let u equal theta, and that means du is just d theta. I let dv be the rest of this thing, sine theta d theta. And I have to integrate to find v, and that's negative cosine theta. Then I apply the integration by parts formula, and I don't want to lose this minus sign out in front, so I have a negative u times v, so that's going to be negative theta cosine theta minus the integral of v du, and v is negative cosine theta, so I'm going to pull the minus sign out in front, making that integral positive. And du is just d theta. Now I'll go ahead and do this integral. The integral of cosine is just sine, and I'm going to distribute this minus sign at the same time. So I get theta cosine theta minus sine theta plus some arbitrary constant. Now I've got to replace all these thetas in terms of x, and I prepared for that back when I originally made the substitution. Theta is the inverse cosine of x. So I have inverse cosine of x times the cosine of the inverse cosine of x minus the sine of the inverse cosine of x plus c. Now one of these pieces is easy and one is hard. The cosine of the inverse cosine, that's the easy piece. They undo each other and I just get x out of that piece. So my antiderivative starts with x inverse cosine x. But the sine of the inverse cosine, that's the hard part. And the way you say this to yourself is the sine of the angle whose cosine is x. And I can draw a picture of this. Angle whose cosine is x. Well, we actually just called that theta in this problem. And if the cosine of this angle is x, that means the adjacent over the hypotenuse is x. And the simplest way to write that is with an x for the adjacent side and a 1 for the hypotenuse. Well, that leaves a missing side that we can solve for, and then we can find the sine of the angle whose cosine is x. So to be explicit about the algebra, I can say x squared plus this missing side, question mark squared, is equal to 1 squared. I subtract x squared from both sides and square root the result, and I find out that my missing side is the square root of 1 minus x squared. And this means that the sine of the angle whose cosine is x, you would take the opposite side, which I now know is 1 minus x squared, and divide by the hypotenuse, which is just 1. And I have the sine of the angle whose cosine is x. So that's just square root 1 minus x squared. Don't forget to write that plus c in your final answer. And we have the integral of the inverse cosine function. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.